world, if that's the case for you, because the exams are just 100 points each, the course is 1,000 points, so that means it's 10% of your grade, which is about a letter grade. So it's not like some classes where the exam, if you miss one, then okay, yes, there's no chance at all of you passing. It's not like that. So that's that. Here's the attendance sheet, by the way. I do have it. I'm going to try to do it every single time from now on. Another question was somebody who had a legitimate reason for making up the exam because they actually were excused and they are scheduled for taking that. I've not put this practice back up yet on Pearson, but I will do that today. Okay, so if that's you, then you have that. All right, let's see. So we're ready for chapter 9 now. Last time we did chapter 8, where we talked about linear versus exponential change, and mostly that's just for your benefit to give you some sort of visceral feel for the numbers. Here's how the numbers feel for these types of problems. So you understand when something's changing exponentially versus linearly, what you should expect from the behavior. Remember we had the surprising example of the bacteria growing in the jar, and it took an hour for them to fill the jar, but they were doubling every minute. And the question is, well, how many jars will they fill after an hour? And I think for most of you, your intuition was, well, it took an hour for them to fill one jar, maybe it's just a couple of jars. But no, it's 2 to 60 jars. 2 to 60 jars, because the number of jars has to double every minute. Now, so after 60 minutes, double 60 times, 2 to 60 jars, because that's how exponential growth is. Almost all of the growth is occurring in the last minute. Right? Half of the total amount is in the last double. Okay, so yeah, these things are just useful for studying various different phenomena. So now we're going to go into chapter 9, where we're going to talk about using math to just model the real world. And so we're going to talk about the connection between things in reality and the world that affect you, and just the math functions that model. Okay, so first thing to talk about is functions. So functions are special instances of relations. So you may remember relations from school, like x is greater than y. Okay, so a number is greater than another. 17 is greater than 6. Okay, that's a relation between numbers. So that's a true statement about a pair of numbers, right? 17 and 6. That 17 is greater than 6. So that pair of numbers, here's a true statement about it. The first is greater than the second. 17, 6. 17 is greater than 6. Okay, so a function is a special type of relation where any time you have the first of those numbers in here, there's at most one second number that corresponds to it. Okay, so it's just a special relationship. But those are the technicalities. The feeling of what a function is you have some dependent variable. So that's something you get to choose as an input to your function. And when you do that, you get to produce an output variable called an independent variable. I'm sorry, I said that exactly backwards. The independent variable is the one you choose because it has a value that's independent of the definition of function. You get to choose it. And you plug it into the function and you get an output, which is the dependent variable. So its value depends on the input. The input, you just choose. It's independent of anything. You choose it. But once you choose it, you can figure out what the output is. That's the dependent variable. Okay, so a function is just a relationship between dependent and independent variables. But it is something that there's a very important restriction on it. For any independent variable, you can have at most one dependent variable. For any input, think of it this way, any input it's a faithful machine. It's never going to trick you. If you put the same input in, it's always going to give you the same output out. You can't put in 5 in and get out 8, but then the next time you put 5 in, you get out 12. Okay? It always gives out the same number. That's a function. A relation is a generalization that you can get out many possible things. Okay, and so we do normally think about inputs and outputs, independent variables and dependent variables for functions. And we think of them as ordered pairs. Okay, and so then if we call x the independent variable, which is just a tradition, and y is the dependent variable, then we can write a function like this, y equals f of x, where f is just the name of the function. Okay? Again, I do the same thing with my kids. I talk about this stuff, and I'll have a function and say its name is Bob. If I put 5 into Bob, Bob gives out 8 or something, you know? So Bob is the name of the function. 5 is my input, so that's Bob of 5. So that would be Bob parentheses 5, and then equals 8. Right? So 8 equals Bob of 5, something like that. So f is just the name, it's the name of the function. X is the name of the v, usually assigned for independent variables, and y for dependent variables. So the value of y depends on the value of x. So here's an example. So suppose it's asking us to just write the function we teach y to the x. Okay, so since you are writing a higher balloon, as the balloon rises, the surrounding atmospheric pressure decreases. Pressure is the dependent variable. Okay, so this is the answer. Pressure is the dependent variable, and altitude is the independent variable. So you go to a pair of variables, it's altitude and pressure. Okay, so what the question is asking us to figure out how to write this as a function, and it's just giving you a situation. You're writing in a hot air balloon, and as it rises, the pressure decreases. Okay, so what's happening is the pressure is a function of your altitude, right? The greater your altitude, the smaller the pressure. So as the altitude changes, it's causing the pressure to change. And so think of pressure as a function of altitude. And you can put this in reverse as well. You can do this exactly in reverse if you want to. We have a lot of research about pressure at different altitudes. Suppose you're in some kind of a giant flying machine, a big metal canister with wings on it, and you're inside of it, and you're up in the air somewhere. And you have a pressure sensor that can tell you the pressure. Then a computer can take all that. It doesn't need to be a very sophisticated computer, but a computer can take that pressure reading and turn it into a guess at your altitude. Right? Because you can see based off the pressure I see, I'm guessing you're at this altitude. That's how altimeters work. Okay? So there's the magic flying metal canisters that we use to get around. Okay, so the last step for this one is say, okay, let's give names to all of these things. So if we let A stand for altitude, so now let's do the second part of the question, which is assign names to our variables and express the relationship. So what names do you want to give the variables? We have distance, so we're probably going to want to call that one Q. Q for distance. Or maybe we should use D. Let's use D for distance. Okay, D for distance. And then river width, what do you want to call that? W, okay? I would say so too. Width is reasonable. And there you go. That's the choice they made here as well. You let D represent distance and W represent river width. And you have W equals F of D. Okay? The whole point of this is just the concept of thinking of one quantity as a function of another, getting between the setup of a real world problem. Next time you find yourself traveling down the Mississippi River and thinking, oh, I just noticed that the width of this river depends on how far south I come. But you know what I mean? Like it's something that's connected to the real world. And you figure out how you can organize yourself for modeling it as a function. Okay, the first step is knowing the independent and dependent variables, figuring out the relationship, where the function goes. Okay. All right, so continue. Okay, representing function. This is basically, there are a lot of ways to represent functions. Here are three that they describe using a data table. So for a data table, you will have oriented either horizontal or you can have oriented vertically. You're going to have one row with your value for your independent variable and another row for the value for your dependent variable. So that if you get the value upstairs, you can bring it downstairs and figure out the value downstairs. Right? Sometimes you represent those vertically. That's actually pretty convenient. I like doing that when we're plotting functions, because if you have your independent variable in the left column and the independent variable in the right column, then if you want to see what points to plot on your curve, the points are just put the pairs left, right. Those are your order pairs. So along the rows, you get the points of your plot. So I like that. Drawing a picture or a graph, that can certainly do it. If you draw a graph of a function, we've seen plenty of them in here before. That can give you relationships between an independent variable, which is usually along the x-axis, the horizontal direction, and the dependent variable, which is usually the y-axis, vertical. All right, you can write an equation. There are other things. There are plots where you can draw maybe an oval indicating all of the independent variable possibilities. Put little dots, label the values, and do the same for the dependent variables, and draw arrows to connect the dots. That's another thing. Hey,
What time is your class over?
it is over. You want it to be over now? It's 2
Wait for test tomorrow.
We're very flexible.
We'll come back to that.
Okay, thank you. All right, let's see. Where was that? Oh, yeah, so yeah. There are many more ways than this. Now, you can also do, as I was mentioning, you can just say, draw a picture of a set, just like a little course of the Mississippi River, and call that 0. I can go, what is that? I don't remember for the Mississippi River. I don't remember for that. It's something I used to have met long ago. 1,700 miles is going to be in my mind, but I don't think that's right. Anyway, yeah. You say it again? 2,300 miles. Okay, 2,300 miles. So, once you get to 2,300 miles, then it's going to be 0. And that's if you assume that there's actually like a straight line thing and not two major tributaries or things like that. Yeah, you get to 2,300 miles, the river stops. So there's nothing else in your domain beyond that, because that's not an area of interest. But then you have all the possible widths of the river. I think the river at its widest is around 3 miles wide. I may be wrong. Can you look that up also, the maximum width of the Mississippi River?
It says 30 feet narrow, 11 miles wide. At lake.
11 miles wide. There you go. So 11 miles wide, that's widest. And that's, I'm not sure if that's a fair measurement or not, but it might be. Let's say 11 miles wide. Okay, so, yeah, so the range is only going to be values from, I guess, 11 feet up to 11 miles, or whatever it was, 8 feet, 11 feet or something to 11 miles. So, you know, that you zoom in, it's say zoom in. You can do that to label your axes because you know what units to use for your input and output values. And if you're running calculator or some technology, you zoom in to view the important part of your function. Then after that, you make the graph. The making of a graph is usually something, almost every time, it's something that just is dependent on data. You have some list of data, some table of data, and you can take those data points and plot them as actual points. And this is like I was saying, if I have my function represented as a couple of columns, say distance south in the first column, width of the river in the second, then I can put those pieces of information together with parentheses around them, and those are my ordered pairs for plotting on the plane. And then I can just plot those points on the plane and make the graph that way for those points. And if it's something that I assume should be a continuously changing value, which is probably what we expect with the width of the river, then you can connect those dots with smooth lines, smooth curves, to get a good approximation of what your actual function is. And that happens all the time. That's easy. When you see graphs of things like the stock market, like the S&P 500 index, you look at a graph head over time, you're seeing things bounce around a bunch. You're seeing the line that you're seeing is the daily points of the value of the index, and then lines connecting those points. That's exactly what you're seeing, and that's what it's suggesting to do, to build a graph. Okay, the last step is not really a step of graphing a function, but it is technically for using graphs and functions. Be aware of what it is that you're seeing before you make predictions based off of it. You could, for example, look at world population and look at a bunch of data points of world population in the past up to the present, and you can see that, oh, the points are low, so low, they get higher, okay, Black Death, okay, they're lower. That's one of my daughter's favorite topics to study for some reason. Bubonic plague. She loves the bubonic plague for some reason. Anything that kills people, she's very interested in. Anyway. Okay, you go up, maybe you have Spanish flu, 1918. Okay, there's a dip. That had a big impact. And then you go up, okay, some wars, some squiggly areas, and then, but it's mostly looking like exponential growth. Okay, but that can only go on so long, right? That can only go on so long. The universe is finite, at least the part that we can access is finite. So there's So, you can't make provisions forever just because it looks like an exponential function now. So there has to be some balance. So that's what the lag is. Okay, so, this is an example to make sure that it is what I think it is. Yeah, that is what it is. Okay, so, hours of daylight as a function. So the number of hours of daylight varies with the season. So we're fixated now on a 40 degrees north latitude. Model will change the number of daylight hours of time. I wonder if anybody's using these slides in Australia. I wonder if they are. I'm just thinking, oh, those jerks. Their globes upside down. Right? With the globes upside down. Those assholes. Most people live in the northern hemisphere. Okay? Okay? That's not a good defense. I don't know. I do think about that sometimes. I've heard people say they go to Australia and see a globe that has north pointing down. I've heard people say that before. I don't know how prevalent this is. I don't know why anybody can really care. I don't know why you would care about that so much, but it's not like they're hanging around and they're just upside down or something. You know? Down is toward the center of the earth, wherever you are. That is down. That's anyway, 40 degrees north latitude. We're just looking at daylight hours at that location and plotting it in terms of time. Okay, so let me ask a couple of things with this. What would you say is your independent variable in this scenario? That there's some function happening here. What is the independent variable for this one? Is I'd say that as time passes, so I would say maybe time. Like you were right, it definitely has to do with this position. It definitely does. But I would say the thing they're measuring two things: time, and they're measuring amount of data, which is also time. But they're measuring time for like when in the year they're measuring the amount of daylight, and then they're measuring the amount of daylight. So they're saying that as the time of the year is changing, you're having a different amount of daylight. So I would say probably the time that's passing is the independent variable, and then the amount of daylight in a day, that would be the dependent variable. It's dependent on. Okay, now it's not clear so far from this what your domain is, but what would be a reasonable choice for a domain for this function? What do you think? Take a reasonable choice. Over what period of time might we be interested in the amount of daylight we have? Yeah. Yeah, between solstices, equinoxes, yeah. Take a year or something here, maybe spring equinox to spring equinox. It could be that you're interested in multiple years, say spring equinox to spring equinox in 4 years. There's a good reason why you might be interested in that also, because there's a slight change because of leap years, right? So there might be a good reason for that. Or maybe you want to do it over the course of 400 years, because at least our current calendars, there's a 400-year cycle in how they work. I don't know if you know about that. 2000 was a leap year. Oh my goodness, yeah. For a second I was about to say, as you know, as you recall, 2000 was a leap year, but you were not born yet, were you? I forgot. You were. You're the only one. Yeah. So 2000 was a leap year. 1900 was not a leap year. It's a multiple of 4, but it was not. 1800 was not a leap year. 1700 was not. 1600 was. 500, 600, 700, right? 900, 1,000, 1,100, so on. Does that pattern make sense? If you're a multiple of 400, yes, you are a leap year. Otherwise, if you're a multiple of 100, not a leap year. So interesting. So 2,100, which I think, surely some of us, probably most of us, will be around then. Hopefully, most of us will be around then. Hopefully not me. I don't want to be around then. That's too old for me. I don't want that. But hopefully many of us are around then. 2,100 won't be a leap year. No leap day. All right, so this game is data. You can say the number of hours of daylight is greatest from the summer solstice around June 21st. Not always exactly June 21st. It can vary 3 or 4 days, maybe even it's possible. About 14 hours of daylight at 40 degrees north latitude. Number of hours of daylight in small winter solstice are about 10 hours. In spring and fall equinoxes, they're about 12 hours. Okay, so that's still data. So this is saying where we already decided time should be our independent variable, so we're giving it the name T. And then our dependent variable is the hours of daylight, so there's going to be like H hours of daylight. And so then your function model says H equals F of T. H equals F of T. F is just the name of your function. F for a function, I guess. F for a function. H is F of T. Okay, so look, they're just making up something arbitrary. We were discussing this. The domain that's interesting for us is all times a day. They're saying, okay, say 3 years. 3 years is fine. That's a reasonable time frame. At least it's enough to establish a pattern, right? So that's reasonable. The range is from 10 to 14 hours of daylight. Why is that the range? Because our data that we collected said to us that the minimum amount of daylight is on the winter solstice, about 10 hours of daylight, and the maximum is the summer solstice, 14. So if those are the minimum and maximum, all of the values lie between those. So our range, and all of them are achievable, I guess is another thing. Again, technically not true. There are finitely many values and finitely many days, and that's an interval that's infinite in terms of number of points. But that's okay. That's okay. It's reasonable. The range is from 10 to 14. Hours of daylight changes smoothly with the seasons. Okay, that's supposed true. So you have finite number of days. The same pattern repeats from one year to the next. That makes it something called a periodic function. Periodic functions are functions where if you look at your domain and you look at the shape of your graph, the behavior of the function on that chunk of the domain, if you shift it over by a certain amount, you get another region in your graph that looks exactly the same. Another region where the function behaves exactly the same on those values. Okay, so for us, that's not too surprising, right? If I take the period of time between, let's say, the winter solstice and the fall equinox, okay, that's 3/4 of a year if I do it in that order, winter solstice to fall equinox. I have some behavior for the amount of daylight. It's at its minimum, it goes up to the maximum, and comes down about halfway, right? And if I shift that over by a whole year, I'll be going to from the next winter solstice to the fall equinox. The shape of the graph is going to be the same. Okay, so that's something true about periodic functions. You take some chunk of it and move it a certain distance, and if you move it just the right distance, that chunk of the graph looks exactly the same. That means you're periodic. Okay? And that's true for all chunks as long as you know the periods. You move it by some multiple of the period, you get the same behavior. Okay, so here's the graphic function. And yeah, they're starting from winter solstice. output might be the temperature that the oven achieves. Okay, 15 million degrees is not going to be a reasonable thing in range, right? So what are reasonable output values? Well, the range that you're interested in. And then, once you know that, if you have data, you can take your data, corresponding quantities for the input value, the independent variable, and the output value, the output variable. Ones that correspond, those are points that you can just plot on your graph. X coordinate, Y coordinate. Those corresponding